We now move on to a new topic called graphs. We're going to give first a precise but otherwise not so great definition of graphs. We'll work our way toward a better definition of graphs, and then we'll give some examples. So a graph mathematically describes a symmetric relation between elements of a set, which means that a graph is simply a relation with a symmetric property. That's something that we have studied, that's something that we understand. So here is a directed graph representation of a graph. And you're entitled to your opinion, but I think that looks pretty horrible. However, as a directed graph representation of a graph, it works great as a relation. Notice how all the arrows between the elements need to go in both directions, and that is because they need to do that for the symmetric property. But you may imagine there might be a better way to express this relation that doesn't have the arrows being so messy. And here is what I think is a better representation of the graph right there. Notice how the double arrows just turned into one undirected connector that nicely expresses those symmetric relationships. Which means that we don't have to express our relation as ordered pairs. We can instead represent them as unordered pairs. The order doesn't matter in terms of the relation. If they're related one way, they're related the other way. If they're not related one way, they're not related the other way. So here is the definition you usually will see for graphs. A graph is a pair V and E. V and E are both sets. V can literally be any set, and it's called the vertex set. And E is dependent on V. It's a set of unordered pairs of elements of V. Those are going to be our edges. So that's our edge set. An element of V is called the vertex. If you have more than one vertex, those are called vertices. And an element of E is called an edge. So usually we represent our graphs visually with the vertices being represented by whatever we're representing the elements of a set by, and then the edges are represented by connectors without arrows, just as we did before. So we have some graph like this. If we want to express this according to the formal definition, we will do it the following way. We will say what our vertex set is. It's the set containing A, B, C, D, and E. And then we'll give a list of all the edges. There's an edge between A and C, so AC is one of the edges. AE is another, BC, BD, and DE. And you're saying, well, wait a minute, there's an edge between C and A. Why don't we include that? Remember, because we're assuming symmetry, the edge AC is exactly as the edge CA. So we only have to list them one way. The other way is implied. So let's say we have a vertex set 1, 2, 3, 4, 5, 6, and 7. And we're going to define the edges this time, not by a list, but by a rule. So we're going to say the edge AB is an edge precisely when A is congruent to B mod 2. So now when I say AB is an edge, that means A is a vertex and B is a vertex, and A and B are connected by an edge, right? And so we're saying the two vertices, which are numbers, we're saying that those are congruent mod 2. That's the only way you can have an edge. So for instance, if you want to do a visual representation, if you had 2, what does 2 connect with? Well, 2 connects with anything that it is congruent mod 2 with, right? So for instance, 2 is congruent to 4 mod 2, so those are going to be connected. 4 is congruent to 6 mod 2, and 6 is congruent to 2 mod 2. Those are all connected. All the odd numbers are connected as well. 1 is congruent to 3 mod 2, 5 is congruent to 7 mod 2, 3 is congruent to 7 mod 2, etc. So just a couple of observations about that particular graph. The odd numbers are disconnected from the even numbers. So not all the vertices are connected to one another by edges, which is fine. There's nothing wrong with that in a graph. And the odd numbers and even numbers are all internally connected to each other. There's no guarantee that if you have some vertices connected that they all have to be connected to one another. But in this particular graph, that's what happens, at least in the two pieces of the graph. So, and by the way, when you have a graph that represents an equivalence relation, which by the way, this one does, this is the sort of visual representation that you might have happen. So I just want to point out a graph can be used for literally any symmetric relationship between any types of objects. So all those symmetric relationships that we talked about before when we did relations, like friendship, like marriage, like sitting next to each other in class. I guess we haven't looked at that example, but it's easy to see that that one is symmetric as well. Countries that border each other, that's also a symmetric relationship. People working together on a project, that's also a symmetric relationship. So keep these examples in mind as you work on the activities. The name of the file is Introduction to Graphs and that's with the PDF files included with this video. For full disclosure, these activities are strictly to help you build understanding. They're not going to be included on the quiz, but it's a good idea to look through them to sort of get an idea about the types of questions that we're going to be looking at with graphs.